Hey guys, I'm here to talk with you all about how we are going to be able to use inscribed angles as well as polygons in this section, right? So I've got inscribed angles and polygons. Forgot to write that down. And polygons. Now, when I say inscribed, all I'm referring to is something that is put inside of a circle, right? So if something is inscribed, then all its vertices are going to be on the edge of a circle. If something is circumscribed, then it goes around the circle, okay? So an inscribed angle, right? This is our first key vocabulary term. An inscribed angle. This is an angle whose vertex is on a circle and whose sides contain chords of a circle, right? So I could, if I wanted to, and I do, so I'm going to, draw a little line or a ray going that direction, then I'll draw another one going off like this, right? And what we have here is the construction of two chords, right? My first chord is here, right? Right there. There's my first chord. My second chord's right here. So I've got two chords that create this, which is an inscribed angle. Clearly, we want to know how we can find the measure of an inscribed angle, and not only that, but we want to be able to reference the intercepted arc, right? So in purple here, I have the intercepted arc. And that is just the arc who shares these little endpoints here, right? The arc contained by the endpoints of that chord that are the end, or that represent the end of that inscribed angle, right? So if I wanted to find the measure of that angle, right, I would say let's label this angle 1. Okay, I've got angle 1. The measure of angle 1, well, that's just going to be equal to half the measure of its intercepted arc. Half the measure of its intercepted arc. So that tells us what an inscribed angle is, what an intercepted arc is, and how we could then utilize that information to solve either for this interior angle, this inscribed angle, or this intercepted arc, right? If I knew the measure of this angle, well, then I could utilize that to solve this intercepted arc, right? And we're just going to plug what we know into these two spots, right? If I know this measure, I'll plug that in, and I can solve for that arc. If I know the arc, then I can plug that in and solve for that missing angle. All right, next thing that we're going to be looking at here. I've got two inscribed angles on a circle, right? I've got inscribed angle right here, inscribed angle. Let's actually go this color. I've got inscribed angle number 1, and I've got inscribed angle number 2, right? We see number 1 there has those blue lines, those blue chords, and they intercept arc DC. And B, angle B there, number 2, also intercepts arc DC. So this is another theorem of ours, and it states if two inscribed angles, right, we've got two of them, 1 and 2, if they intercept the same arc, DC, then we can say that those angles are congruent, right? We can say that angle 1 is congruent to angle 2. Why? Because they share that intercepted arc. For those of you who care, that is Theorem 10.8. If two inscribed angles share a common intercepted arc, then those two angles must be congruent. All right, moving on. Now we got ourselves a nice little circle that has a triangle, and if we're looking at this, we can see that this triangle is right, and it's right because, hey, look, right there, I've marked it as such, okay? So we have an inscribed polygon. Triangle ABC is an inscribed, right? Meaning it is inside the circle. It is an inscribed triangle. Right? All vertices are on the edge of this circle, and the circle passes through all those vertices, right? So we call that an inscribed triangle. And then we can say that circle D is circumscribed around triangle ABC, right? So these are two statements that we can say here. Triangle ABC is an inscribed triangle because there's a circle that passes through all of its vertices, and circle D is circumscribed. It goes around triangle ABC. So this theorem that we're going to be looking at right here, 10.9, theorem 10.9, states that if a right triangle, so we have a right triangle here, ABC, if a right triangle is inscribed in a circle, then its hypotenuse, AC, is the diameter of the circle. If a right triangle, I should say, if a right triangle is inscribed in a circle, then its hypotenuse is the diameter of the circle. Not only is it the diameter, right, we can say that it passes through the center of the circle, right? It passes through point D. AC, the diameter of the circle, has to pass through the center of the circle, and we can see that AC is, in fact, the hypotenuse of this right triangle. And you can look here, if I move B, right, if I move B anywhere along this line, right, let's say I put B here. All right, let's put B prime like that to show. And I draw these sides. Look what we've got. We still have a right triangle there. We still have a right triangle that's being made. So I could even move it over to let's go with a different color here. I could move it over to here. Oops, didn't want to erase that. That's all right, we can come back with it. Boom. If I wanted to move it over to here, right, if I want to put B here, right, I could connect B to these points, and look, we still have a right triangle. So it doesn't matter where that point B is, right? As long as the hypotenuse of that triangle is that diameter, you're going to have a right triangle, right? So that gives you the converse of theorem 10.9, right? If a triangle is inscribed in a circle, and it just so happens that its hypotenuse, or one of the sides, passes through the center of the circle, then you know you have a right triangle. All right, next part, theorem 10.10. Theorem 10.10. This one says, hey, if we've got, again, we've got a polygon that is inscribed in a circle, right? It's inscribed in this circle. We've got point, 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 point. All of those vertices are on the edge of our circle. And in particular, we're dealing with a quadrilateral. So a quadrilateral can only be inscribed in a circle if and only if its opposite angles are supplementary. Okay, so we're going to write here, we're going to say a quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. So, for this specific problem, right, that's going to mean, well, that means that angle 1, if I were to add, I'm going to use a better color here for this. If I had, let's go orange, angle 1 plus angle 3, those are going to have to be equal to 180 degrees. Angle 4 plus angle 2, right, these are opposite angles. Those are going to have to add together to give me 180 degrees. All right, if they don't add together to give me 180 degrees, then I cannot say that they are, in fact, supplementary, and therefore can't say that this is a quadrilateral that's been inscribed in a circle. Something would have to have been off. If you hear a low grumbling, that would be my dog growling at a man outside my window, which is not as creepy as it sounds. All right, guys. You guys let me know if you have any questions, and I'll be around.